Hi everyone, welcome to Preparing Your Agents for the Iceberg Age. I promise this Iceberg Age will go better than last one. We'll all survive. Who of you remembers, raise your hand, who of you remembers a couple of years ago there was a case in the US, two New York lawyers, some of you remember this case, two New York lawyers submitted a legal brief generated by ChatGPT. It was entirely fabricated. All the case numbers were fake, hallucinated. There were case titles that were created by the chatbot. But it turns out the lawyer actually asked the ChatGPT, is it a real set of cases? And the bot responded, yes, they're real. So the lawyer submitted the legal brief to the court. The court accepted, but the opposing counsel did their work and figured out all fake. So why did it happen? Oh, and it all ended with a case dismissal and a large fine. So why did that happen? Why 2 years ago were we able to hallucinate legal cases? Well, if you think about how chatbots were working 2 years ago, they were using a large language model. That's the infamous LLM abbreviation. And this LLM was trained on a corpus of training data, typically a couple of hundreds of terabytes of data. The process of training would take months. By the time the LLM was released, it was already dated. And of course, it was not trained on everything. So when a user would ask a question, generate a legal brief for such and such case, and give me some references to existing legal cases, the chatbot would call the LLM. In the best case, it would use a technique called RAG, Retrieval Augmented Generation, or CAG. That's a more recent technique. And the textual output would be produced, and that was it. If only did our chatbot actually search a real legal case database. They exist. It's very simple to go to a system called LexisNexis. That's a thing in the US. You type in description of your legal case, and you will either get cases or you will not get cases. But the chatbot didn't know how to do it. So this led the industry and some of us to realize, I think we need to complement knowledge in LLMs, which can be dated and incomplete, with some factual and recent info. So today, how the way chatbots work, if you use ChatGPT or if you use other tools, they use things like agents with tools. You still have a LLM, and it will accept a prompt from a user. But instead of answering right away the question, it will enter into a reasoning loop. Who of you kind of know approximately what reasoning is? Some of you. So it's a loop where the agent consistently makes progress based on a prompt. And the progress will involve calling other tools. It can involve calling a web search on an external API. It can involve querying an analytical database or an operational database. And this process will go on until the chatbot gets a response from the LLM that has final answer in it. At that point, the answer will be finalized. It will be potentially stored. It's optional. It will be stored in a system called memory, together with the prompt and the output, and the circle or the cycle continues. So who am I to be talking to you about all of this? I used to work right in this office. I also managed to work at Databricks and Google. I'm currently a co-founder in a startup, a Berlin startup called Tower. And we're building a serverless Python platform for ETL workloads and AI inference workloads for teams who are too busy to manage their own infrastructure. So in this talk, I've already talked about the motivation, how bad the past was. Let's talk about the beautiful future. We'll discuss how to use agents with analytical and operational databases. We'll make a reference to Iceberg because that's the future in the analytical world. We'll look at the architecture of an agentic system that provides access to analytical data stores, and we'll do some takeaways. So how do we complement knowledge in LLMs with recent and factual info? Tim Scarl, the host of MLST Talk, recently said something that really resonated with me. He said, LLMs are basically databases. And of course, we are sitting right now in an office of a database company, and half of you here, if you show them a brick, they will find a way to describe it as a database. But if you think about it, it actually makes sense. LLMs are compressed versions of knowledge. They contain data. And let's look at a open source, well-known LLM called Llama 4. What happened during training? Well, someone took 30 trillion words. That's approximately 150 terabytes of data. And they trained it for many months, 9 months in particular for this particular LLM. And at the end, they ended up with a set of files that were less than 1 terabyte in size. So if you calculate and do the math, it's a 200x compression. And for those of you who were interested in information theory, if you have a 200x compression of a data set, of course it will be lossy. But it's also, we are okay with this because it allows us to write questions to it that kind of look like they're generated by a human. And it excites us. And we are weak, we are humans. Now, if you look at a analytical DB or an operational DB, you are dealing with a much larger data set. I'm not saying we should be using it for training. I'm just saying it's there. There are tens of petabytes, hundreds of petabytes. We met a customer recently. They have 1,000 petabytes of data. Most of it sitting still on tapes. And the knowledge in the analytical DB space is more recent. It's not months old. It's maybe an hour old or a day old at most. And in the operational DBs, it's a couple of milliseconds. And of course, there's no compression per se. There is some storage compression going on, but data doesn't get compressed in a lossy way. What you put into an analytical DB or an operational DB, you can get out in the same form. And because of this, query results are deterministic and they are not, and they're factual. So, I mean, it kind of makes sense to bring together LLM knowledge in LLMs with facts in analytical and operational DBs. We understood based on our motivational example, it's important to bring the creative part of LLMs with the factual knowledge contained in a database. Wouldn't it be nice to be able to store everything in one place? Some of us actually ask this question. Disregarding the fact that entirely different serving environments, LLMs typically have to be fully loaded in memory, and we can't do this with a large data warehouse. Have you ever tried replacing a popular database? It turns out, for the last 10 years, the top 3 database technologies in the world have been things that your parents have used, my parents have used, you are using. So it's Oracle, SQL Server, and MySQL. They remain the same. There are some movements in popularity, but they stayed the same for the last 10 years. The new kid on the block, Postgres, new quotation marks, took 10 years just to get position 4. And the newest kids on the block, that's Snowflake and Databricks, are growing faster, but this is logarithmic scale. So the difference between what's on top and even our favorite Snowflake is still 10x. And if you think about it, Oracle is used in many, many use cases, right? So Databricks and Snowflake are growing fast, but if you kind of think about all the other places where Oracle is deployed, there are just 10x more deployments. So it's super hard to replace something in the database world because the applications are relying on them. Therefore, it's safe to assume agents, if we want agents to be smart and use factual and recent data, they will have to use what's out there already. So analytical DBs and operational DBs will stay with us for a while. And this also means then we should probably pay attention to what is going on in the world of analytics. And since you are in a meetup about Iceberg, you probably have heard that the coolest trend in the analytical world is the adoption of Apache Iceberg as the storage technology. So I'm not going to be talking about why Iceberg is being adopted so fast. We've seen good examples, why it makes sense for Echo and others. I will talk a little bit about what we think are the requirements for database technology to be able to support agents with analytical data. I think the first big requirement that will be important for agents being able to utilize analytical data is the support of a significantly higher throughput rate than anything humans have thrown at analytics. Why is that? Well, first of all, if you think about a question that a human might ask a chatbot, why is this stupid example of why is my sales spiking, or why is this interesting new pattern happening? This typically translates in a series of breakdown queries. You run the select queries, they break it down by dimensions, they try to find certain spikes, and when they see unusual behavior over time, they report back with, oh, in this particular geography and this particular product category, there is a change, and this is why your sales are spiking. So agents, first of all, have much higher stamina of throwing these queries. Human analysts will eventually give up, and they will be satisfied with the first set of answers. But agents have almost unlimited resources, and they will continue analyzing until they analyzed everything. So there's more stamina in agents. And secondly, agents don't have the institutional memory of what they've asked in the past. A human analyst will probably has done this analysis before. It's not the first time some executive is asking this question. So they've known the patterns, they know the patterns, what to look for. An agent doesn't know. So because of this, there'll be many more queries against the Iceberg data lake from an agent than there are from humans. The other big requirement, I think, for agents to be able to help, for analytical stores to be able to help agents, is data access security. In effect, humans delegate their work to some random algorithm, and humans want their data to be protected. Things like masking sensitive columns or restricting raw sets to just the data sets that the agent needs to answer the question are very, very important. And so data access security becomes important because it's a delegated set of work. How does Iceberg measuring up for these requirements? In terms of throughput, read throughput, Iceberg is actually doing very, very well because it relies on the horizontal scalability of underlying object stores. For write QPS, unfortunately, Iceberg is not super great, but the community is working on it. And it's also probably not very important for the agentic case because agents will typically read from analytical stores, then they will be writing into analytical stores. The other important requirement, data access security, it's also a space where the Iceberg community is working on. Not every catalog supports, and typically catalogs are responsible for data security. Not every catalog supports row filters and column masks. There are some that do, head tip to Lakekeeper and Unity catalog. There are emerging standards for fine-grained access control, OpenFGA, and role-based access control. So it's going to be solved soon. Now, let's look into some systems that actually allow agents to access and work and benefit from analytical databases. I'm working on one of them, Tower. We are a platform that provides building blocks that you can use to build pipelines, tools, and agents. We have these building blocks of tables, models, and catalogs. We have horizontal services we offer, orchestration, team collaboration, alerting, we call beams. So you can end up building a very nice tower out of them. And in Tower, everything revolves around applications. You can build 3 types of applications: pipelines, tools, agentic tools. I'll show you what it means. and agents, and we rely on open source libraries. We collaborate with open source vendors on providing this functionality to our users. For example, DLT Hub, DuckDB, Polars, and others. When you develop an agent in Tower, I would suggest you use a agentic framework. I prefer LangChain. And when you develop an agent, there are basically 4 things you need to do. You have to declare your tools. These are the things that the agent will call to do certain tasks. Super important, textual descriptions of tools. This is how the LLM will know whether to call the tool or not. Then you initialize the model, the prompts, and the memory systems. You create agents, and you invoke it on user input. I wanted to show you a quick demo of how this all works. And in the demo, we're going to look at a backend agent that is responsible for maintaining a lakehouse table with up-to-date information for a set of stock tickers. So it will upload. Its entire responsibility is to pump data from an external web source, information such as open and close price info and volume for a stock into a lakehouse table. And so with this, wanted to show you these textual descriptions and prompts. This is basically the magic behind agentic frameworks. If you kind of look inside of, or if you look a little bit deeper into a prompt that your agent will use, there are placeholders where you can put the descriptions of your textual of your tools. I'm giving my particular agent 2 tools. One is able to check the availability of data inside of a lakehouse table. So it does a query against an Iceberg table. The other tool is able to get info from an external source and store it into Iceberg. And I need to create English descriptions for all of this to work. So with this, let's look at the demo. I have to pull my little recording over there. How about this? I have a QR code that you can scan if you would like to see the demo of the agent. Yeah, sorry. Well, maybe just proceed with the slides. So in the demo, I wanted to show you how to go from developing the agent to deploying it to Tower and then actually seeing it in action. But my demo gods are not cooperating. There are a couple of other cases where you can use agents together with Tower. We have a customer, Cogni. They're using us to first onboard data from external documents and then store them into Iceberg. And the second use case they use us for is whenever a customer, and they're building knowledge systems, knowledge graphs. Whenever someone wants to search against a knowledge graph, they cognify the data in an Iceberg table and then start serving searches from this knowledge graph. All right, so what are the takeaways? Hopefully I was able to show you a little bit how the failures of the past, the chatbot failures of the past could be addressed by new techniques where tools are onboarding recent data and factual data and complements the data of the knowledge in LLMs. Because the analytical world is moving towards Iceberg, agents need to be able to speak Iceberg, and there are agentic frameworks that enable access to analytical data. We think the future of agents is bright. We still need to work a little bit on on that future, but I think it's bright. We think they'll be eventually running in lots of places, in the public clouds, in your cloud account, on your laptop, on your phone. But to get there, we have to address some of the blockers, and they are being addressed. These are the three main blockers that used to be true in the past. Proprietary models, you couldn't really use proprietary models unless you were using the proprietary services too. This is being addressed by open source models becoming more and more accurate and actually exceeding now proprietary models. You have Llama, DeepSeek, Gamma families of models. Then model sizes, that used to be a big problem in the past. As models got more sophisticated, they grew in sizes, billions of parameters, hundreds of gigabytes of storage space. There are techniques now, quantization and distillation, that reduce these sizes and these models such that you can run a pretty sophisticated and accurate model on your laptop or on a desktop. And vendors are releasing new versions of consumer-grade hardware. You're seeing a couple of examples from Apple and from NVIDIA. These are desktop boxes you can put on a desk, and they have enough RAM and GPUs to be serving pretty sophisticated open source models that fit there. One of the remaining big blockers is the difference between GPU stacks between different environments, locally, on premises, and in the cloud. For example, locally, we tend to use either Mac, Apple Silicon, or NVIDIA consumer hardware with our Windows machines. On premises, there's a mix of AMD, Intel, NVIDIA, and in the clouds, NVIDIA is the more popular choice. And so how do we, and unfortunately, the GPU drivers are so different that you can't have the same code running everywhere and using the same code. So there are a couple of approaches that have been tried before. Some folks try to Dockerize the applications. Some folks try to bring consumer hardware to the clouds. You see here an example of 100 Apple Mac Studios deployed into a rack. Docker containers, unfortunately, don't really work well on Mac hardware and when you try to use GPUs. We at Tower, we are working on a different approach. We are working on a portable Python runtime. We give users virtual Python environments and they work everywhere. So that has been working pretty well for us. If you would like to talk to me about any of the stuff that I just shared with you, get in touch with me. Would love to chat with you about this. And yeah, so it's we think there's a lot of potential in the stack, and agents coming together and using analytical data is the future.
Thank you. Okay, so let's take just one question before we break.
Thank you for the presentation, and you highlighted the access issues with agents, and I'm interested into costs. So because we provided access to agents for different databases such as Snowflake, Google, BigQuery, and so on, and is there any features in Tower so you can see, okay, my agent spent this amount of money for these queries in Snowflake and Google, because without these limits, you can burn money like, I don't know how much.
We offer you two choices in Tower. You can either use serverless providers, for example, Together AI to call, you can host, I guess we're talking about agents accessing storage. So Tower's approach is we give you either a serverless environment or you can use us in a hybrid mode. And hybrid mode means you can run the app itself on a runner in your environment, accessing your data storage. You will have to figure out good pricing from your cloud provider, but this is kind of your responsibility. You run compute and storage in your environment. We just take care of orchestration and the control plane. That's option number one. Option number two, we have a completely serverless environment where we take care of storage and compute and so on. Mostly targeting customers and users who don't want to worry about manageability. You're right. Without putting good guardrails on quotas on usage, you can burn through quite a bit of storage get and put requests. We have a quota system. We allow you to limit your usage to a system where you don't spend all of this funding on it. But I think the bigger answer is we give you the option of running Tower in your own infrastructure, which should be saving you quite a bit of costs.
Perfect. Serhii, thank you very much. It was awesome to see what is possible.